Hello, everyone. Welcome to Climate Change AI Virtual Summer School 2024. My name is Dongxue Zhang, and with me today is Donna Vakalis. We are TAs for this lecture. And today we'll talk about AI for social sciences, economics, and policy, part 2. Climate Change AI is a global nonprofit that catalyzes impactful work at the intersection of climate change and machine learning. And for more information, please visit our website. And during the lecture, please use the chat for general comments and Q&A feature to ask questions. Please upvote the questions that you are most interested in. Questions with more upvotes will have a higher chance of being asked. And please use show captions to enable captions. And today's lecture will be held between 10 to 11 p.m. And the title of lecture is Empirical Estimation of the Influence of Weather and Climate on Socio-Economic Outcomes, given by Professor Johnson. And Professor Johnson is an environmental economist and scientist with a background in agronomy, climate science, remote sensing, and machine learning. He's an assistant professor in food and resource economics at the University of British Columbia. He was a postdoc fellow at the Harvard Data Science Initiative and the Center of the Environment. And he earned his PhD in agriculture and resource economics from UC Berkeley in 2019. His research focuses on developing methods to estimate anthropogenic impacts on climate and global socio-environmental systems. Let's welcome Professor Johnson giving us his presentation.
Ready to go? Cool.
Yes.
Hi, everyone. It's a pleasure to be here. I'm just going to pull up some slides. Yeah, so we'll be taking questions throughout, but mainly kind of a pause in the middle in a space between topics. The broad question kind of organizing the thoughts today is how will climate change influence human well-being? And that's obviously a very large and multifaceted topic. And so we can kind of think of breaking it down into two sub-questions. First, how will greenhouse gas emissions and climate change influence the environment? So how will climate change influence temperature distributions, rainfall distributions, cloud cover, and in turn sunlight, as well as soil moisture? So you can kind of think of climate as a large range of variables that could influence well-being. And then so the first question is, how is the environment going to change? And the second question is, how will changes in the environment in turn influence human well-being? And so this first part is kind of within the realm of atmospheric science and earth sciences. That's often estimated using Earth system models, projecting the world forward to see how these environmental factors are going to change. And we're kind of going to make reference to that, but not touch it directly in this talk. What we're really going to focus on here is the second question of how do changes in the environment influence different aspects of human well-being? And so that's what we're going to focus on today. And so we can see that we could combine these two and to say sort of the change in well-being with respect to an emission of CO2 can be decomposed into the change in well-being with respect to a climate variable like temperature, and then how temperature is going to change with CO2. And so we'll be kind of estimating this partial here throughout the rest of the lecture. So just to give you a bird's eye view of how this process usually works, the goal is kind of to understand how if you shift from one distribution of weather or climate, so one climate is kind of what you expect to get, it's probability distribution of weather. As you shift from one distribution of, say, temperature to another distribution of, say, temperature, how does your expected distribution of the social outcome variable change? Maybe the social outcome variable here could be human mortality rates. Maybe it could be agricultural productivity. Maybe it could be sleep quality. the same kind of structures are used to estimate a variety of social outcomes. So you start with these climatic distributions. We don't really experience the climate, we experience day-to-day weather. And so that's kind of depicted in this time series here. One thing I want to point out is that weather has many different temporal frequencies. So there's kind of high frequency variation day to day. There's slightly lower frequency variation moving from fall to winter to spring to summer to fall to winter to spring to summer. And so we'll be using and talking about different frequencies of weather variation throughout this lecture in terms of identifying the influence of different of climatic factors on different social outcomes. The way that these weather realizations are connected to realizations of the social outcome can be thought of through a dose-response function. And so a dose-response function is what we're going to be spending some time talking about estimating today. And that is essentially kind of a lookup between the value of a climate variable, say temperature, and the expected value of the social outcome variable, say agricultural productivity or human mortality. And so reading this, say it was human mortality, you could see that human mortality decreases with, say, increasing temperature up to a point after which increasing temperature leads to increasing mortality rates. And so this weather time series, when projected onto the climate variable, when projected onto the dose response function, creates a time series of expected social outcomes. And so this dose response function provides a way to link kind of today's climate to today's distribution of the social outcome, and in turn, a future climate to a future distribution of the social outcome. And so for the rest of the talk, we'll be exploring how to estimate these climate social outcome dose response functions. And so we can learn this relationship between social outcomes and climatic variables like temperature, soil moisture, et cetera, by analyzing their historical associations. And so, for example, we might ask, within a state over time, how do higher than expected mortality rates associate with higher than average temperatures? Or within a country over time, how do lower than expected crop yields associate with lower than expected soil moisture? And so by analyzing many changes in the social outcome variable and climate variable over time, we can begin to kind of sketch out the relationship between the two, which we call the dose response function. So let's go through a few examples of what this looks like in the literature. So this is a dose response function of how agricultural productivity in the US, specifically corn yields, respond to changes in daily temperature. And so you can see that increasing temperature increases yields up to a point around 30 Celsius, after which further increasing temperature leads to large yield losses. And so combining this response function with this same kind of process we just looked at up here, so kind of just replacing this dose response function with that yield dose response function and analyzing changes in climate projected by climate models, these authors found that average yields are predicted to decrease by 30 to 46%, but by the end of the century under one of the slowest warming scenarios, and decrease by 60 to 80% under some of the more rapid warming scenarios. So that's how you can kind of use these response functions to link changes in climate to changes in the social outcome. And we'll complicate this prediction a little bit towards the middle of the lecture. You can also see the influence of, for example, yields not on temperature on yields, but sunlight on yields. So this is looking at how changes in cloud cover influence agricultural productivity. And here you can see an additional day of cloud cover relative to clear sky days increases maize and soy yields by around 0.5%. The specific response function is for 3 hourly treatment. So that's how multiply this by 3 and you get around there. But the point here is just that it's not always temperature. You can look at other variables as well. Moving away from agriculture, this is an example of a dose response function that was estimated for GDP, so gross domestic product. And here the authors used repeated observations over time for countries around the world to sketch out how, on average, GDP changes as temperature changes. And so that then allows you to project changes in GDP under climate change using the similar same process. People have estimated these things for a ton of different variables. This is conflict. I'm not going to go into the details here, but these are the types of outcomes that we're going to try to learn how to estimate today. How does this fit within kind of a broader policy picture? One way these response functions are kind of brought together and used in policy is through estimation of the social cost of carbon. The social cost of carbon is the monetized value of all future net damages associated with a 1 metric ton increase in CO2 emissions. Essentially, what it is just if you were to emit 1 extra ton of CO2, how bad would that be in dollar terms for global well-being? And so you kind of do things similar to what we were just talking about. Under a certain economic pathway, you figure out how much the climate is going to warm. That gives you changes in temperature and sea level rise. Push that through damage functions, and then do some economic massaging, and that eventually kind of allows you to aggregate these sector-specific damages to agriculture or human mortality, et cetera, into a single value of the damages from climate change. The social cost of carbon forms the basis of regulatory cost-benefit analysis. So it's kind of when a new law or policy would change emissions, the social cost of carbon is often used as kind of an input into the total costs and benefits of a new policy. And it kind of can form a foundation for carbon policy as well. So, but I want to emphasize that the dose response function for a lot of social outcomes is not known. So there's a lot of things that we would love to know how they respond to changes in weather and climate, but kind of we just haven't done the research yet. And so I think it's an exciting field to be in because there's a lot of low-hanging fruit here, both on the methodological development and just on sectors that we still need to analyze. So how do we do it? So how to estimate these dose response functions. So for a social outcome Y and climate variable C measured in a given location I and time period T, we can use linear regression to learn the function F that maps variation in weather onto variation in the social outcome of interest. And so that can be as simple as kind of a linear regression between the social outcome and the climate variable of interest. Maybe you regress agricultural productivity in a bunch of counties and years on temperature in those counties and years with some appropriate controls. Obviously, it's a little bit more complicated than that. And so we'll go through two main challenges to kind of estimating these types of dose response functions in ways that are useful and appropriate. And so the first challenge is identifying a causal effect. We want to estimate the relationship between the social outcome and the climate variable, such that if we make projections of how the world is going to change under climate change, kind of we get the correct influence of just those changes in the climate variable. And second, this is more of a data limitation. Often the social outcome variables that we're able to measure are fairly coarse spatially or temporally. Average, for example, average mortality over at the national level. And so we need to be careful to be able to estimate the nonlinear response between the outcome variable and the climate variable of interest correctly. But let's tackle these in turn. First, let's dig a little bit into identification of a causal effect. So to accurately predict how climate change will influence social outcomes, we need to recover the causal effect of, say, temperature or another climate variable C on the social outcome variable Y. regressions of y on c directly could be confounded by variables emitted from the regression that co-vary with both y and c. And so, for example, the northern US is generally both richer and cooler than the southern US, but there are many other factors that differ between the two other than climate. You can think of kind of in the agricultural realm, natural soil quality endowments. You can think about their different histories. There's a lot of things that are different between the northern and southern US. Using spatial differences in temperature and wealth to predict future climates would implicitly assume that the north will become more like the south as the climate warms, which could be not true for a variety of reasons. So what are ways to address this? We can think of kind of the ideal scenario where we could approximate a randomized control trial by having two identical Earths, or maybe even a series of identical Earths, where we would treat one Earth by increasing its temperature and then compare that with the control Earth. And the difference between those two would be the causal effect of warming on the social outcome of interest. We're kind of doing this current experiment with our planet now, but we don't have a control Earth to compare it to. So what can we do in practice? In practice, we can simulate this with a natural experiment where a region in one year can act as a control for the same region in a different year with a different temperature treatment. And so this kind of approximates a randomized control trial because year-to-year weather is arguably as good as randomly assigned with respect to most social outcomes. So instead of comparing New York to Virginia, you could look within New York over time and compare New York in 1991 to New York in 1992. And so that's kind of using variation within a location over time and arguing that year-to-year variation in weather is as good as randomly assigned. So how do we implement this statistically? It's commonly implemented using a panel fixed effect regression design. And so let's break that down word by word. So a panel is just a term for the type of data observations you have. And specifically, it means repeated observations of your social outcome variable and your climate variable in multiple locations over time. So you can think about it as many different time series stuck together. If you think of kind of one time series of Y and X observations as a straw, you can think of kind of a bundle of straws as your panel of observations, where you have many different straws with observations over time. So that's what a panel is. A fixed effect is a set of intercepts, which are often kind of high dimensional and usually control for either time or space. And so a common fixed effect is to, for example, include an intercept for each county, for each spatial region in your data. If you have county level data, maybe you would include an intercept for each county in the model. What the fixed effect does is it essentially demeans each time series, meaning that what you're left over with after you've included the intercept is only variation over time within each location. And I'll show you that graphically in a moment. And then finally, the last part of this panel fixed effect regression is the regression part. And here we're going to be using ordinary least squares regression. And we'll just briefly discuss penalized models towards the end. So again, the common approach here is to kind of isolate temporal variation. So this variation within panel units over time by including a set of spatial fixed effects that absorb all variation in your outcome and climate variable across space. And so you might implement that something like this, where you would learn the model of, say, mortality in a given state and year is some function of temperature plus a fixed effect for state. And so that would mean you're looking within a state in the variation in these variables over time. Put another way, you would estimate f, this nonlinear function, by comparing temporal anomalies in Y with temporal anomalies in C. You can also, of course, include temporal fixed effects, such as linear time trends, and then you would be soaking up variation associated with time rather than space. And so as a quick practice question here, I won't have you share the answers, but just kind of write your answer down to yourself. Let's think about, we just talked about what inclusion of a spatial fixed effect does. Now let's think about if we can extend this to what in turn does a temporal fixed effect do. So inclusion of a temporal fixed effect, for example, a fixed effect representing an intercept for each year in this panel fixed effect regression design, would either one, effectively demean all observations within each time period t, so that f is estimated using only spatial variation within time periods, or two, effectively demean all observations within each location I, so that f is estimated using only temporal variation within locations. I'll give you maybe 30 seconds to think about that, and then I'll share my answer. Okay, so in the chat, I'm seeing, yeah, a mix, but mostly number ones. Yeah, so I agree with mostly number one. Yeah, so number two is what a spatial fixed effect does. So a spatial fixed effect demeans all observations within a given location, so that f is estimated using only temporal variation. On the flip side, a temporal fixed effect effectively demeans all observations within a given time period. So maybe a year fixed effect, that would be an intercept for each year, effectively demeans all observations in that year. And then you identify the effect using spatial variation within that time period. This might be easier to a little bit easier to see visually, and so this is a sample of data from a project that I was working on to estimate impacts of weather variables on COVID-19 growth or transmission. And so the outcome variable here was the growth rate of COVID-19 cases. And the X variables we were looking at were temperature, humidity, but primarily UV. So we can focus on UV as the treatment of interest here. What you can see is that across different locations, we looked globally, but this is just two example locations. You can see a time series from Paris, France, and Santiago, Chile. You can see that a lot of the variation in these data is actually across space. These are quite far away in their y-axis, and so a lot of variation in the data is just simply the fact that Santiago, Chile has a higher UV than Paris. But what we want to do to approximate this natural experiment is really to identify off of the high frequency variation, which is probably less associated with kind of potential confounders than the spatial variation between Chile and France, which could also incorporate kind of differences in culture, which could induce differences in how people interact, maybe even just cultural differences that could in fact impact transmission rather than the influence of UV directly. And so the first thing we do is we include a spatial fixed effect, which demeans both of these time series as well as the outcome. And so what you see is that the time series for Santiago, Chile and the time series for Paris, France are both now centered at 0. Next, what we do is we include temporal trends to remove this slow frequency temporal variation of these trends, which could also plausibly be associated with issues such as, changing policies with respect to school openings and things like that. Once we removed the low frequency temporal trends and the spatial fixed effects, we're left with this nice kind of clean identifying variation where you have some days that are relatively higher UV than expected, then lower than UV expected, then treated, then control, then treated, then control, then treated, then control. And that's the type of kind of plausibly random variation that we want to use to understand the effect of, in this case, UV on COVID-19 growth. And in this paper, it actually had a pretty substantial impact on the results. So if you looked only in the cross section, you recovered a positive effect between increasing UV and increasing COVID-19 transmission. But we know from laboratory studies that UV directly kills the virus, and we know from basically from a scientific standpoint, we shouldn't expect a positive association between the two. And so once we clean the variation to what we argue is as good as randomly assigned, we actually recover a strong negative effect of UV on the COVID-19 growth rate. And so once you include these different fixed effects to isolate this plausibly random variation, in this case, it actually changed the sign of the estimate. Okay, so as a summary, fixed effects are useful for isolating the variation in the climate variable that we as researchers and practitioners have to believe is as good as randomly assigned. So the art here is to think about the situation at hand, the specific relationship that you're seeking to estimate, and to think, okay, what type of climatological variation approximates a natural experiment, and then how can I design the fixed effects such that that is the variation left over that's actually used to estimate the effect. I want to highlight two discussion points here. The first is the difference between the effects of weather and climate from a construct point of view. It's often easy to argue that short run variation in weather is as good as randomly assigned. So whether today is a hot day or a cold day, within a given week of the year is to somewhat random, right? January 1st, 1991 could be hotter or colder than January 1st, 1992. And that's to some degree random, exogenous to or outside the system of interest. And so I think we can get pretty good estimates of the effects of weather. But really what we care about is, for projecting climate change, is the effect of climate, which is inherently the effect of longer run changes in climate. And so one of the challenges, ongoing challenges in the literature, is how do we get causal estimates of these longer run changes in environmental variables when those could be more associated with otherwise omitted confounders. And so I think that's an interesting direction that the literature is currently going. And there's a variety of approaches to estimate that, which I'm happy to discuss further if you're interested. Another important challenge here is that spatial and temporal fixed effects are good at capturing, filtering out the spatial variation or these lower frequency temporal variations, but there can still be high frequency time varying variables that could confound the analysis. So a lot of people have studied the impact of temperature on agricultural productivity. In some of my recent work, I showed how temperature can be correlated with other climate variables such as soil moisture, and that really changes the understanding of how temperature itself impacts agricultural productivity. And that can have a really pretty economically substantial impact on our understanding of how yields will change, whether we're thinking about temperature alone or temperature and soil moisture jointly. So even other climate variables themselves can be emitted variables in the setting, in that they kind of covary with temperature even at high frequency. Okay, so I'll stop. I'll pause a minute for questions here before we jump into the second challenge. Is there anything that people want to hear about?
Yes, Professor. There is a question from Anne about slide 12.
Slide what?
12.
12?
Yeah.
Okay, yeah.
The question is that the discounting is used here because the interest of climate research is to estimate the present value of future damage caused by climate.
So I think maybe that's here. Yeah, so I skipped over this because there's a lot of complexities within how you actually estimate the social cost of carbon that are a bit beyond. I'll say discounting in here at a very high level is simply because losses in the future are often valued less than losses now. So essentially, I would prefer to have $100 today rather than you giving me $100 in 10 or 20 years. That $100 is just worth more to me now. And so there's kind of it's commonly assumed that damages in the future are less bad than damages immediately. And so that's kind of what this notion of discounting is. I also saw in the chat that there was a question more about the different ways to estimate the effects of climate rather than weather. Is that something I should dig into a little bit? Sure. I'll do it just briefly. So there's a range of strategies. One option is to just look kind of purely cross-sectionally and regress average temperature on average social outcome values. That's kind of, from a construct point of view, one of the best ways to get at the relationship between climate and the social outcome, where climate really is these long-run temperature or long-run soil moisture or something like that. The issue there is then you're using purely spatial variation, and you might be comparing things that are very different. And so you can have confounding variables, like in that northern US, southern US example that I give, that kind of cause the relationship to be related to things other than actually the climate variable and the social outcome variable of interest. What other approaches that people have developed to kind of deal with that a little bit is to look at spatial first differences. And so that's kind of comparing two locations, rather than comparing all locations across space, you only compare really close by neighbors. And so there it's, you're comparing like this place to this place, then this place to this place. I don't know if you can see my hands. You compare only neighbors by including like a spatial pair fixed effect. And so that maybe if you believe that the confounding variation has low spatial frequency, then identifying the effect only off of spatial neighbors can improve your interpretation as the effect of causal. And so whether you do that or not really depends on whether you think the high spatial frequency variation or the low spatial frequency variation is more as good as randomly assigned. And this is where it's always going to kind of depend on what you really are worried about the confounders being. Another approach is to look at kind of do trends in climate on trends in climate. So you can see have places that are places, like how do places that have been warming compare, like essentially regress the trends on the trends. So have places who have a positive trend in warming, do they have a positive or negative trend in your social outcome? And so there's kind of, all of this is about thinking about the process and thinking about what type of variation do I think is as good as randomly assigned? Is it high frequency temporal variation, low frequency temporal variation, high frequency spatial variation, low frequency spatial variation? What type of treatment is as good as randomly assigned, and what type of treatment is kind of is valid in construct with how I want to make a prediction? Yeah. Okay, so yeah, so now let's jump into the second challenge, which is we often want to know the local and potentially nonlinear response of an individual unit, say an agricultural field, or the impact of mortality on kind of an individual impact of temperature on mortality rates of an individual person, so that we can make accurate projections about the impact of climate change, but also the spatial distribution of climate change. A challenge here is that we often observe only aggregated, so county, state, or sometimes even national level observations of the social outcome variable. And so, for example, we might want to estimate the response of maize yields to temperature and soil moisture globally. But globally, we only have national level yield observations. And so you have this very coarse resolution measurement of your social outcome. And so this could be a challenge because if the local response were quadratic, think about like an inverted U shape, and half of the nation's crops were below the optimal temperature and half were above the optimal temperature, then for small variations in historical temperature, you might actually estimate no effect because half the crops are doing better and half the crops are doing worse. If, however, you have a large future increase in temperature, that could generate substantial net damages because, you know, the places that are getting warmer start to get shallower on this U shape, and the places that are getting hotter, their effect becomes steeper and steeper. So that's how kind of not getting the local nonlinear response could cause a challenge for the total impact. It's also true that kind of coarse response functions also can miss the distributional impacts, where maybe within a country, cooler fields are benefiting and hotter fields are warming. So if you want to kind of know who the winners and losers are, it's also beneficial to be able to estimate a local nonlinear response function. And so the idea here is that for outcomes that are aggregates, either across time and or space, you can recover the local nonlinear response of the social outcome to the change in climate variable by relating the aggregate outcome to the aggregate nonlinear temperature exposure in a linear model. So let's break this down. Let's take, for example, let's take the example of crop production and in a given county I and year T. And so you observe county level agricultural production. But what you want to know is the local response, say at the 5 kilometer by 5 kilometer field level, which will denote F. So we have county I, year T, and field F. And so we want to estimate this first line here of yield in a given field and year as some nonlinear function of temperature in that field and year. Let's take kind of a standard quadratic, a standard functional form. Let's assume F for the sake of simplicity is quadratic. And so Y, F, yield in a given field and year can be expressed as some coefficient beta 1 times temperature plus beta 2, another coefficient beta 2 times temperature in that field squared. Now what we can do is we can sum over fields F within each county I. And so we have the sum over all fields within the county for Y. And then the sum of the linear and quadratic field level temperature exposure. What's nice is that the sum of the production within all fields is the county level production. So now we've gotten this left side into something that we actually observe here. We have the county level production in a given county I in ERT. What we have on the right here is aggregated field level temperature exposure with linear and quadratic terms. And what's nice here is that because this is a linear model, we can pull the coefficient outside of the summation. What this does is this kind of transforms this into a regression model that we can estimate, where now our features are the sum of the field level temperature over the entire county and the sum of the field level temperature squared. And so importantly, if we have fine level temperature observations, which we tend to have measures of environmental factors at much finer resolution than we do measures of social outcomes, because you can get satellite-based measures of surface temperature and soil moisture and things like that. So it's just easy. We tend to measure the environmental factors better. If we have these fine resolution environmental factors, then we can aggregate those up after taking nonlinearities to the county level, and then we can estimate this equation here. The key thing is that the coefficients recovered from estimating at this aggregated county level are identical to the coefficients that you would have recovered had you estimated it at the actual field level. So using aggregated outcomes, we can still recover the local nonlinear effect of temperature on the outcome. This is just repeating that. And so conceptually, this approach works because of the linearity of the model. So you can kind of interchange the coefficient and that summation there. And so I think it's an interesting question of, could you do something similar to this with a more nonlinear model like a regression tree or something? Though I will emphasize that you can still recover a nonlinear response of the social outcome variable to the climate variable by just kind of lifting the environmental variables into a feature space that allows for estimation of a nonlinear response. And so here we used a polynomial basis. You could also use linear splines, restricted cubic splines, or whatever kind of basis you want to best represent the climate variable. Yeah, I mentioned this earlier. Generally, estimates are made at the resolution of the climate data, which tends to be finer resolution than that of the social outcome data. And we did this simple derivation for spatial aggregation, but temporal aggregation kind of works the same way. So often in an agricultural setting, you have growing season measurements of productivity, but what you're interested in is kind of the daily effect of a temperature shock. And so you can do that temporal aggregation in the same way as we did the spatial aggregation. So here's another practice question: is true or false? Is the sum of the squares of temperature aggregated the same as the square of the sum? And we'll give 20 to 30 seconds again for this. Yeah, so people are fairly unanimously saying no, which I agree with. And essentially, the point here is that, and if you want, you can convince yourself with kind of two values, say 2 and 4, square them, average them. That's not going to equal the square of their average, which is 3. And so the key point here is that by taking nonlinearities of the variable at the finest resolution that you have, that captures the impact of extremes of extreme temperature treatment on your social outcomes. So learning a model that is kind of featurized like this, rather than squaring the average temperature, includes the information, if you imagine you had kind of, includes the information of extremes on your social outcomes. So you could imagine you have a country like the US where you're simultaneously having a heat wave and a drought. Those extreme temperatures are going to be represented in high values of temperature squared. Whereas if you had kind of ideal middle conditions, that's going to be represented as low values of temperature squared, relatively so. And so the main idea there is that by appropriately aggregating the climate variables, specifically calculating nonlinearities at the finest resolution possible, you're more accurately capturing the distribution of weather that actually goes into the production of your social outcome at the, say, field scale. And then that aggregated field scale information is what actually determines your social outcome at the aggregated level. Okay, so in summation, we can address the first challenge of causality using fixed effects to isolate variation in the climate variable that is as good as randomly assigned. And second, we can estimate local nonlinear responses if the social outcome variable is an aggregate across time and space, by appropriately aggregating our climate information to the same level. And so at the end of the day, many models kind of putting this together take a form similar to this, where you might regress yields in a given country I in year T, crop yields in a given country I in year T, on the linear temperature exposure, the quadratic temperature exposure, location-specific dummies or fixed effects to control for spatial variation. So you're identifying effects within a location over time because you're including these. And then because you're including a linear time trend, you're identifying effects within a location over time after accounting for a time trend. You could similarly include a time fixed effect, like a year fixed effect or something like that. But this is kind of the general structure that's used to estimate the types of dose response functions that we saw earlier. There are a lot of complexities to estimating these types of models. One extension that I want to raise here briefly is the notion of heterogeneity. And so so far, we've been estimating an average effect across the entire panel. Maybe that could be an average effect globally or an average effect across the US. But it's very likely that F, this relationship between Y and C, differs across space, across time, or across other attributes like between rich and poor areas. And so this heterogeneity in F is often modeled by including interaction terms into the regression. And so if you wanted the effect in a, say you had state level mortality data across the US over time, you could allow the effect to differ by state by including a dummy variable for each state and interacting that with the response function of interest. What this is going to do is it's going to essentially estimate a different response function for each state. And then that's going to really increase the complexity of your model. And so you could penalize the coefficients on these kind of on this spatial heterogeneity effect to kind of only allow the function to be complex as is useful for predicting the outcome out of sample. That brings us to notions of model selection. When doing model selection, it's common to select models only on the kind of what we call the identifying variation or the good variation that that's left after you remove the variation associated with the fixed effects. So if you remember the COVID example here, this would be the identifying variation after you've kind of removed, you've anomalized everything, and that would be the variation on which you want to do the model selection because that's the variation that you kind of believe is due to the actual, or might more likely to be unconfounded. Yeah. And just an example of this type of heterogeneity, here we can see a global estimated response function for the impact of changes in temperature on human mortality. And then we can see these smaller administrative unit responses in the shaded colors. And you can see there's a lot of heterogeneity in kind of the damages from extreme coldness and the damages from extreme heat on mortality rates caused by temperature. And here we can see that kind of this right slope here plotted on the graph. And you can see there's a lot of variation across space in how different locations respond. So I think that's another direction that the field is going, is saying, okay, let's not just estimate the average effect, let's estimate the effect for different locations. Okay, so kind of summing up here, we've gone through some key challenges for estimating dose response functions between social outcome variables of interest and climate variables. And those can allow us to understand how changes in climate translate into changes in the social outcome. And that translation is conducted by kind of projecting these distributions of climate onto the dose response functions, which will allow you to translate to the distribution of the social outcome of interest. And at a higher level, this is kind of this is summarized and used in policy by converting these damage functions in combination with climate models and some economics into estimates of the social cost of carbon. I want to emphasize here that damage estimates are currently not available for all sectors of the economy or determinants of well-being that are affected by climate change. So many difficult to quantify sectors, such as ecosystem services and human migration, have yet to be included in estimates of the social cost of carbon. And so I think there's kind of a lot of low-hanging fruit here, given increasing availability of data, computational resources, and really kind of engaged people such as yourself to estimate these types of dose response functions. And so I'll just make a quick plug that I'm currently accepting applications for graduate students and postdocs. So if you're interested in doing this type of work, please check out my website and reach out. And I'll leave you with an open-ended question of what is a social outcome that you think might really be affected by climate change and that really matters to human well-being. Maybe that's sleep quality. Maybe that's how people migrate within and across borders. Maybe that's how productive people are. Maybe it's how connected people are to their friends in some way that climate change might control. So I'd encourage you to think about what social outcomes might be of interest to you and how you might estimate that effect. You know, what types of confounders might you be worried about, and how might you isolate variation in the climate variable that's as good as randomly assigned. So with that, I'll end and take any questions.
Good. There is a question from the audience regarding to slide 23.
Okay, let's go to slide 23.
Yes. So here, the question is that why do we assume that the coefficients for each country I are equal amongst them? Why wouldn't them be different?
Why wouldn't the coefficients be different?
Yes.
So here, so I guess that's part of I think there's two questions you could be asking. Like, one is, why is it okay to pull this coefficient out here? Why is it maintained the same? And that's just kind of mathematically from the fact that you can, move the coefficient outside of the summation. So multiplication and summation, we can pull this outside. There's another question here, which is like, why are we assuming that the response function is the same across all I? And I think that is an assumption that we can relax, and that we can relax specifically in this kind of heterogeneity discussion that I talked about here, where you can, instead of assuming a single response function for the whole region of interest, you can estimate different response functions for each I. A challenge there is, I guess so theoretically, you could just estimate a separate regression or a separate function in each individual spatial unit. The challenge there is you're going to start losing power. you're going to have fewer observations to estimate each effect. And so it's kind of a trade-off between sharing information across space and allowing the effect to differ across space.
Yeah. Another question about could you elaborate on the graph you showed regarding the impacts of the soil temperature and the humidity on crop yield?
This one?
Yes, I think so.
I think so. Okay, so essentially here, the idea is to try to separate the influences of temperature and moisture on agricultural productivity. And so commonly what is done in the literature is to regress crop yields on temperature and on rainfall, with rainfall addressing issues related to moisture and temperature addressing issues related to temperature. And that's done because rainfall is relatively easy to measure. You can kind of put something out and see how much falls into it, whereas soil moisture is a more difficult measurement to make globally and historically. What we did here was to include soil moisture in the model because we think it's a more accurate representation of the actual water supply available to the crop. Essentially, what falls from the sky is not necessarily what's available for the plants to suck up. And so we compared two models here, one in which you regress yields on temperature and precipitation or rainfall, and that's shown in the dotted lines, and one in which you regress temperature, sorry, where you regress yields against temperature and soil moisture, and that's shown in the solid lines. Importantly, rainfall ends up being not that good of a predictor of the actual moisture available for crops. And so what happens is that in the temperature and precipitation model, the temperature curve sucks up or incorporates a lot of the damages due to dry soils in the actual temperature response. So if you interpret this dotted line here, you can think of that as increasing temperature, but also increasing dryness. And so what you can see is that the damages conditional on precipitation are substantially larger than the damages conditional on soil moisture. And so including soil moisture into the model allows you to predict more of the variation, but it also allows you to separate the damages due to low soil moisture from the damages due to extreme heat. And so that's why the heat is less damaging once you account for soil moisture, because you're no longer also baking in damages from low soil moisture into estimates of extreme heat. In turn, because soil moisture and temperature are likely to change differently in the future, that leads to different projections of the impact of climate change on yield. And so a key notion here is kind of if two variables are going to change the same under climate change, then we can kind of just use one as a proxy for the other and just model one and move forward because they're going to keep co-varying together. The key thing with temperature and soil moisture here is that it's important to separate them because changes in temperature historically associate with changes in soil moisture differently than temperature and soil moisture are going to change under climate change. And so it's important to tease those out because they don't maintain their historical association in the future.
Yeah. Thank you for your answer. So I think we are running out of time, so I think that we need to end this lecture. And we appreciate all the great questions from the audience. And thank you, Professor Johnson, for the amazing lecture. And thank you all the audience for being here. And see you at the next lecture. And by the way, I have put the feedback form on the chat. Please fill it out. We appreciate your valuable feedback.
Great. Yeah, thank you so much for having me.
Thank you, Donna.
Pleasure.
Bye.